We are very happy to have Damián visiting us and give an insightful seminar on the subject Multiphoton and side channel attacks in Mistrustful. Quantum philosophy, right? We're going to trust each other, I guess. Damián, he received his PhD from Cambridge University in 2014 under supervision of Adrian Pence. And since then, he's worked in different institutions in Oslo and Paris. And he returned to Cambridge University in 2018, right? And he's currently a research associate there. So we are very happy to have him with us to tell us more about his work. Okay, that's thank you.
Thank you. Yes, thank you very much for the introduction and for the opportunity to visit your group and give this talk about my work. Thank you. Thank you everyone for coming. So this is a working collaboration with Matthew Bosio, Adrian Caballes, Eleni Diamante, and Adrian Kent. And I would like to thank in particular my founder, the UK Quantum Communications Hub. So Mistrustful quantum cryptography is a large field and one of the major applications in the global quantum internet, envisaged for the global quantum internet. It includes important tasks like bit commitment, coin flipping, oblivious transfer, and secure computations. In this paper, we have identified new multiphoton attacks on practical implementations of Mistrustful quantum cryptography with photonic setups, and we have shown that some previous implementations were vulnerable. We also illustrate the power of these attacks with an experiment and discuss side channel attacks. So let me begin by making a comparison and stressing the differences between Mistrustful quantum cryptography and quantum key distribution. So in quantum key distribution, we have Alice and Bob working in collaboration and trusting each other, right? And there is a third party if against which they are playing. In Mistrustful quantum cryptography, usually we only have two parties, Alice and Bob. There is no eavesdropper. So Alice and Bob still collaborate to implement a task, but they don't trust each other. So in particular, we will focus here in the case where Alice is dishonest. So we will assume that Bob is honest, but Alice is dishonest. So we're gonna focus on photonic setups. So Alice has the photon source. Ideally, it's a single photon source, but it will be only approximately single photon. Because Alice is dishonest, she can change the source to her advantage. So she can replace that by a source that can send multiphoton pulses, for example. On the other hand, in quantum key distribution, Alice doesn't have any interest in changing the source because she is honest. So she will have a single photon source, approximately, of course, as agreed with Bob previously. The security problem due to multiphotons in quantum key distribution is different to the multiphoton attacks considered here. In quantum key distribution, usually the problem of multiphotons arises because if could apply a photon number splitting attack, right? So if Alice sends a pulse with more than one photon, if could, in principle, and also in practice, split the pulse in the various photons and measure the different photons in different bases. And in this way, she can learn information about the key. In mistrustful quantum cryptography, and in this presentation, we are not referring to those attacks. Instead, Alice, because Alice controls the source, she can learn some information about Bob's measurement choice, which should be private, by manipulating her source. Okay, this will be clear in the following slides. Examples of mistrustful quantum cryptography are bit commitment, coin flipping, die rolling, oblivious transfer, secure computations, quantum tokens, etc. These are envisaged as applications in quantum networks and the global quantum internet. So this work focuses on this task. This is a primitive that is used to implement more complex cryptographic tasks. We call this task private measurement of an unknown qubit state. So this task is as follows. Alice sends Bob a random BB84 state, although we can consider more general states too. Bob measures the state in one of the two BB84 bases. Bob chooses randomly and secretly which bases to measure. All right. So this bit beta must remain private. That's the security condition we focus on here. Bob sends a message to Alice reporting whether a measurement outcome was produced or not. So if we had a perfect setup where there were not any losses and Bob had perfect detectors, there wouldn't be any losses, right? So Bob wouldn't have to report any losses, and this would be ideal because we wouldn't have this security problem. But in practice, many setups have high amount of losses, and the detectors do not have perfect efficiency. So Bob has to report losses to Alice so that the protocol works correctly by restricting the task to those particular pulses that were detected. So the condition of security against Alice is that she shouldn't learn any information about Bob's bit, or in other words, the probability that she guesses the value of beta should be arbitrarily close to 1/2. As I said before, here we assume that Bob is honest, so we only care about dishonest Alice. Okay. So, as I mentioned, because we need the third step in which Bob reports losses to Alice, we need to, well, Bob has to be careful in choosing how to report a successful measurement. We are going to focus on this particular setup in which Bob has two detectors. These are threshold detectors, meaning that they do not indicate the number of photons activating a detection. These are the more practical detectors, the standard detectors used. So there are various ways in which Bob could report a successful measurement to Alice. As we will discuss, these open different attacks. And I will describe some of these attacks according to the various reporting strategies for this particular setup with 2 detectors. And to be precise, we can consider that Alice encodes the quantum state in polarization, although our analysis applies more generally. So what are multiphoton attacks? These are attacks in which Alice does not send the photon pulse as agreed with Bob, having approximately 1 photon. Alice can, because Alice has dishonest, she can send an arbitrary pulse with possibly with many photons. This can be entangled among themselves if Alice wishes so. This can also be entangled with an ancilla held by Alice. So in general, Alice can prepare an arbitrary quantum state and send this to Bob. And she will try to learn Bob's beta, meaning the measurement choice of Bob, from the message that Bob sends to her. Okay, in general, these are multiphoton attacks. So now I will discuss some multiphoton attacks for some particular strategies by Bob. So first, a very simple strategy by Bob is to report measurement as valid if only one detector clicks. So if only one detector clicks, Alice can apply this attack. She can send a photon pulse with a large number of photons in the same state, the same BB24 state. Let's say the 0 state. In the ideal situation in which there are no imperfections in Bob's setup, all this, if Bob measures in the computational basis, all the pulses, all the photons, sorry, in the pulse will go to the same detector, the detector corresponding to the state 0, right? So that a detector will click with very high probability. On the other hand, if Bob measures in the other bases, in the Hadamard bases, a very large number of photons will go to the first detector, and also a large number will go to the other detector. So both detectors will click with high probability, right? So if Bob only reports single clicks as valid measurements, if Bob measures in the same basis of Alice, only one detector click, and Bob will report that as a valid measurement. If Bob measures in the other bases, both detectors will click, and Bob will not report that as a valid measurement. So then this means that from the message M received from Bob, indicating whether the measurement was successful or not, Alice can learn Bob's measurement choice, right, with very high probability. In practice, we will have imperfections, and so this attack will not apply perfectly, but we have demonstrated this attack experimentally. This was performed by my colleagues Matthew Bosio, Adrian Caballes, and Eleni Damanti in the University of Paris. And we see in this plot that in that attack, by having Alice by sending a pulse with increasing average photon number, Alice's guessing probability increases and gets very close to unity, right? So this is a real problem that has to be addressed in experimental demonstrations, experimental implementations of Mistrustful quantum cryptography tasks. So how can we try to address this particular attack? Well, a simple thing to do is not reporting single clicks as valid measurements, instead reporting a measurement as valid if at least one detector clicks. So if one detector clicks or both detectors click. In this case, we have shown that if the detector efficiencies are exactly equal, we obtain perfect protection against these attacks. However, in practice, we will not have exactly equal efficiencies, but we can use attenuators to reduce the difference between the efficiencies. Okay, so then in this case, when Bob reports valid measurements, those in which one or two detectors click, and there is a difference, still a difference in the detection efficiencies, we call multiphoton attack to any strategy that Alice applies of this type of sending some arbitrary multiphoton pulse to Bob that uses Bob's message to learn some information about Bob's measurement choice. So whenever Bob applies this reporting strategy or reports a measurement as successful, when Bob detectors click with high probability, when with high probability Bob reports a measurement as successful if both detectors click, we call this multiphoton attack too. Okay, when we have a difference in the detector efficiencies as we expect in practice. Let me now move to a different strategy, which has been used a lot in the literature. This is called symmetrization of losses. The idea here is that Bob tries to symmetrize the losses by equalizing his reporting strategies. This can be done by discarding detections from the most efficient detectors or bases. This was introduced in this paper, and it was claimed to be a technique to guarantee security against Alice. And we have shown in our paper that indeed this can offer very good protection to Bob in the case that Alice's pulse has 0 or 1 photon. Right? But the problem is that, of course, Alice is dishonest, so she doesn't have to send a pulse with 0 or 1 photon. She can deviate arbitrarily from that. She can send an arbitrary multiphoton pulse, and therefore, as we will see later, the security guarantee of this paper does not apply, right?
What's the difference between this just putting attenuators in front of the detectors to balance the efficiencies?
Yeah, it's a good question. So if you put attenuators, you can, putting attenuators can help for this strategy for symmetrizing losses by trying to make the detections close to each other. This is slightly different because the idea is to discard. So even after we put some attenuators, we will we'll try our best to equalize the efficiencies, but still we won't achieve equally. We won't achieve exactly equal detection probabilities. There will still be some difference. So this strategy, what it does is, after trying with attenuators, we discard some events. So let's say the detection probabilities are 51% and 49% in the different detectors. So we throw the 1% extra of the highest detection probability, so that at the end we get 50-50%. That's the idea of this strategy. It's just discarding some extra detections. Yeah, is that helpful? Yes. Yeah, and intuitively that should guarantee security, and that's the intuition that they use in this paper. When you have equal detection probabilities, you would think that you achieve security, but the problem is that might work for the particular setup that was agreed between Alice and Bob, that particular source that gives you those particular probabilities. You can equalize those probabilities, but Alice can change the statistics of her source, and by changing the number of photons, those equal detection probabilities will not be equal anymore, because Alice can send 2 photon pulses, or 3 or 4, 5, etc. All this will change the statistics, and we will not be able to equalize the probabilities for arbitrary statistics of Alice. Yes.
Very basic question. Why would Alice want to send multiple photon pulses? So Alice already knows what state she's generating. Alice want to intentionally let some third party get that information in this case.
Sorry. Could you repeat your question? I didn't hear.
My question is, what Alice gained from sending multiple photon pulses?
What does Alice gain from sending multiple photon pulses? Oh yes, good question. So the statistics, the probabilities of detection at Bob's side will depend on the number of photons that Alice sends. So, for example, in the multiphoton attack 1 that I mentioned, she increases the detection probabilities she makes the detection probabilities very high by sending a multiphoton pulse. So more generally, she will affect the detection probabilities by sending different number of photons. And because Bob reports to Alice whether there was a successful measurement or not, from that message, she gains some information about the measurement basis. So Bob's detection probabilities will depend on the basis of his choice and also on the number of pulses. So by changing the number of pulses, she can learn some information about the basis from Bob's message.
So we don't want Alice to know the measurement.
Yeah, we don't know. Alice shouldn't know Bob's measurement choice. Yeah, that's the security condition we try to enforce. Yeah. Thank you. So now let me move to a broad class of reporting strategies. These are called probabilistic reporting strategies, where Bob accepts a measurement as valid with some probability that depends on which detectors click. So it could be only the first detector clicking, or the second, or both detectors clicking. And it could also depend on the basis chosen by Bob. So we have these various detection probabilities, right? And so Bob will report a measurement as valid according to the various detectors and the basis of his choice with this particular probability. That defines the strategy, these probabilities, okay? And the previous strategies are special cases. Of these probabilistic reporting strategies. Another strategy that is a particular within this class is a trivial reporting strategy where Bob does not report any losses. So basically, Bob accepts all measurements as valid, independently of which detectors click. This is a a strategy that offers perfect protection against arbitrary multiphoton attacks because, well, basically, Bob is not sending any information to Alice, right? Bob sends the message m equal 1 with the same probability or more, or even with unit probability. So for all detection events. So basically, he's not sending any message to Alice. So Alice cannot learn anything from that message because it's always the same message, right? So ideally, we would like to implement this trivial strategy where Bob does not need to report any losses, and we would get rid of these multiphoton attacks perfectly. But the problem is that in order to implement this, we would need extremely good setups where there are very small amount of losses and we have very good detection efficiencies. Because otherwise, with high losses and small detection efficiencies, as happens often in practice, the protocol would not work correctly. Okay, so when we use this primitive to implement more complex cryptographic tasks, those more complex cryptographic tasks would not work because Bob would have a lot of errors, right? If he has a lot of losses and he doesn't report any losses, the protocol would have to work on all the pulses, even those which he didn't detect. So for those which he didn't detect, he would have to guess the outcome, and this would give errors with high probability. Therefore, the protocol will not work. So this means that, unfortunately, most of the time, in many situations, we cannot use this strategy. So we will have to use some other reporting strategy for reporting losses, and we will have the multiphoton attacks problem. Okay, so our main, let me skip this. Our main result is then that actually for this broad class of probabilistic reporting strategies, the only strategy that guarantees perfect protection against arbitrary multiphoton attacks is the trivial reporting strategy where Bob does not report any losses. Any other strategy will have that loophole in which Alice can learn some information about Bob's basis using some multiphoton attack. Okay, so in particular, this implies that symmetrization of losses does not guarantee the claim protection because this strategy is a particular probabilistic strategy, probabilistic reporting strategy, right? So this is important to note, to clarify, because this technique of symmetrization of losses was claimed to guarantee security in this paper and has been used in various experimental demonstrations of mistrustful quantum cryptography to guarantee security. It has been used as a technique to guarantee security, but that claim does not apply, right? Because it follows in particular from this result. And this implies in particular that various tasks using that a strategy of symmetrization of losses are not secure. Some of these papers have used symmetrization of losses in their security analysis. Some others have not. But we, independently of that, we have shown in our paper that some of these tasks are open, are vulnerable to the multiphoton attack one. This one in particular, which is the paper who introduced symmetrization of losses, this has explicitly said that they didn't report multiple clicks as valid measurements. So this uses a different setup, not the setup one with two detectors that we have been discussing here. This uses a different setup with 4 detectors. But the attack applies also to that, yes?
Can you go back to the previous slide on the main theorem?
Yes.
I'm still trying to understand the main theorem, right? So if box because you use a different, so there are different efficiency, and then so how does the training strategy program very secure? Can you see how why would that be secure?
So it's a question.
So I mean,
what?
yeah, theorem, but so if the
Yeah.
efficiency is different, I thought because when the efficiency is different, it will be insecure. So why? So when it is different, why would the trivial Republican strategy give us security?
Why the trivial reporting strategy?
Why is it secure?
Why is it secure?
Yeah, because it is different, right? So I mean, so the 0 and 1 have different efficiency, right? So why would that be?
It obviously reports it's probably sending nothing at all. There's no information you need that it's knowing what is
And why? But still, you have bias in the result, right? So the measurement result is bias, right? Yeah, it's not done to us, but still, if you implement a code, or I suppose you want to do some, I don't know, like random number generation or bound flipping, like the result is not demanded. So you can that be a problem.
The thing is that, like, even if bot didn't receive the photon, he will also report that he received the photon.
Yeah. The idea of the trivial reporting strategy is Bob would accept all pulses as valid, even if the detectors didn't click. Yeah.
Okay, but can what obviously do a random?
Oh yeah, that would depend on how this primitive is used in the cryptographic task. But usually, yeah. Yeah. Yes.
But then I don't know. We will go Russell up because I mean there's laws in the channel.
Yes, exactly. That strategy most of the times would not work because we will have losses. But in an ideal situation where our losses are very small, let's say we have Alice and Bob close to each other, so there is no a big distance. They are close to each other. There is some loss in the quantum channel, but that might be small if they are very close. If we have very good detectors, there are some detectors having 80% efficiency or more. If we have this kind of very good detectors, we would achieve very small losses, maybe 10%, even less than 10% maybe. And for those kind of very good setups, that trivial reporting strategy might still be a good option.
So have you done some simulation on how much loss you can tolerate? What sort of detection efficiency would be acceptable? I mean, so we can discuss.
We haven't made any simulation, but because the problem with the losses could be in the correctness of the protocol, right? If Bob does not report any losses, those pulses that are not detected, usually Bob would have to guess the outcome, right? So that would increase the errors. So for many tasks, this will depend on which task, but usually we need to have a small amount of errors so the protocol works correctly, right? So ideally, Bob shouldn't have any errors, right? But in practice, the protocols are designed so that there is a small amount of errors that can be tolerated. So this depends on the various tasks, but it could be of the order of 5%, for example, 5-6%, 3%. Maybe there are some protocols working even with 8% error. So if Bob had, let's say, 10% of losses only, so he guesses the outcomes with probability 1/2, so we will have about 5% of errors. If the protocol tolerates 7% of errors, then that protocol would work, right? Yeah, this is something we will try to do in future implementations. We're working on some practical implementations of some mistrustful quantum cryptographic tasks, and we will, I think we will use the trivial reporting strategy because the setups are very good, and so we can have a sufficient amount of errors even if we don't report the losses. Yeah, so I think it's possible in practice, but it will depend specifically on the task.
Okay.
Yeah. Thank you for the question. And so because well, as I was mentioning, these are examples of experimental demonstrations of mistrustful quantum cryptography tasks that are subject to multiphoton attacks. Some are subject to multiphoton attack 1, this one in particular, because they do not report multiple clicks as valid measurements. And a generalization of the attack discussed here for 2 detectors applies to 4 detectors, and therefore they are subject to this attack. This one, for example, explicitly say that they report multiple clicks as valid measurements, so they are covered against multiphoton attack 1. These do not say whether they report multiple clicks or not as valid measurements, so we don't know. But here the important point is that it's important to clarify, right? To know which detections you are considering as valid or not. And well, these are vulnerable to the other type of attacks, attack 2, because of course they cannot guarantee the detection efficiencies to be exactly equal. right? And there was no more analysis in that sense. Okay. Now I'll just a brief discussion on side channel attacks. This is not something we investigated deeply in our paper, but we have some discussion on this. So the idea of side channel attacks is that Alice controls further degrees of freedom. So in the protocol, Alice, yes, of course.
Before we get onto that, I'm trying to understand, are you suggesting that if my detectors are balanced, then I'm secure against these multiphoton attacks? Even if I have lossy detectors, as long as they're balanced, I'm secure against them? Or
If the detectors are balanced,
yeah.
if they have equal efficiencies. If they have perfectly equal efficiencies, yeah, there is a way to be secure against arbitrary multiphoton attacks, which is what we call reporting strategy 2, in which Bob reports measurement as valid if one or both detectors click. If he reports one detector clicking or the two detectors clicking as a valid measurement, that covers all attacks. But if the efficiencies are exactly equal, yeah, if they are not exactly equal, you don't satisfy them. Yeah, thanks for the question. Okay. So yeah, as I was saying, side channel attacks, Alice exploits degrees of freedom that were not agreed with Bob as part of the protocol. So in the protocol, let's say Alice and Bob agree that Alice would encode the quantum states in the polarization degrees of freedom. But Alice might encode information in other degrees of freedom. For example, the wavelength or the angle of incidence or intensity of light and so on. So various other degrees of freedom she can exploit to obtain information about Bob's measurement choice. So these are side channel attacks. And my understanding is that there is not currently any perfect protection against arbitrary side channel attacks. There are various approaches to deal with side channel attacks. For example, measurement device protocols. These are good solutions against multiphoton attacks and side channel attacks on the measurement devices, but they are open to attacks on the source, right? We have fully device independent protocols that ideally should be secure against arbitrary side channels on the source and also on the measurement setup, but they have some implementation problems, and they also have loopholes. The loopholes in Bell experiments, for example, detection efficiency, detection loophole, and locality loophole. These are the main loopholes. Fortunately, these have been closed simultaneously in experiments reported in 2015. But still, these experiments have other loopholes. Yes,
So
yes.
Suppose I know they exist, right? But do they apply to your problem, right? So for a specific protocol, right? Like, I don't know, determinant or quantizing, I mean, do they apply to your protocol?
Yeah. Yeah, well, this is our discussion is broad. We are not focusing on some particular task or protocol. So it's a broad discussion. I can mention, for example, in terms of let's say relativistic, there are some relativistic bit commitment protocols that were designed to be device independent. So they apply the Bell experiments, the violation of Bell inequalities to guarantee security in a device independent way. This is a work by Adrian Kane and Emily Adam. They have this device independent relativistic bit commitment. So if there were loopholes in that implementation, in that Bell experiment, then their security claims would not apply, right? Because the idea is that the violation of Bell inequalities is what gives the security. But if there are loopholes, that violation of Bell inequalities could be explained by local hidden variable theories. I think the security will not follow. Yeah. Yes. Yeah. There is another loophole that is not discussed so much in the literature called the collapse locality loophole, which has not been addressed properly. I think only one experiment tried to address this, and in particular what are called loophole-free Bell experiments of 2015 are still subject to that loophole. The idea of the collapse locality loophole I just mentioned briefly is that we don't know when a quantum measurement is completed because we don't know when the collapse of the quantum state is completed. So it could be that in Bell experiments, the measurement results are reported to be obtained at specific times. For example, when the photons enter the detectors, but we don't really know when the collapse is completed. It could be that when the photons enters the detector, the photons are still in a superposition, right? The photon is still in a superposition of being in detector 0 and detector 1. There hasn't been collapse yet. And then there is maybe some current, electrical current in the detector 0 and detector 1, and that's still in a superposition. So we don't know when the collapse is completed, right? If the collapse is completed much later, then it could be that the measurement actually is completed much later than what is reported in the experiments. So it could be that the measurements are completed at time-like separations instead of space-like separation. So that's a loophole that has not been addressed. Yeah. Yes.
Can we say like the photon enter the detector and then the signal to the computer or something, some electronic device, and then there's some sort of time cap. So from there we know exactly what time the device they got the check that be.
Yeah, well, I think usually what I understand from the experiments, usually we know when the photon enters the detector, and so we could consider that the time when a measurement outcome is obtained. But yeah, but in the measurement postulate of quantum theory, we don't really know when the measurement, when the collapse.
Delay in the reporting of the events and the actual event itself, and this delay we don't really know for sure.
Yes. Yeah, we don't know when the superposition collapses. Yeah. Of course, this loophole cannot be closed completely because we cannot know for sure when the collapse is completed, right? We could have everything in superposition. But a way to reasonably close that loophole, as was proposed by Adrian Kent, was to assume that when a human can distinguish between two outcomes, we could assume superposition has collapsed. Well, yeah. Yeah, I mean, there has to be some assumption, right, on when. Yeah, but the idea with the human distinguishing outcome is that I think it's about 0.1 seconds when we can distinguish. We see something, but we see a 0 or 1, but we take about 0.1 second to take that consciousness of that. So he argues that 0.1 second, that should be a time that we could assume for the collapse to have been completed. It could be much earlier than that, but we could assume that. So that means that Bell experiments could need the distance between the wings to be 0.1 light seconds, which is about 30,000 kilometers, about 1/10 of the distance between the Earth and the Moon. So we still have a way to go to perform those experiments, but I think they will be implemented in the near future. Yeah, sorry, I deviated a lot from the side channel attacks. A countermeasure that provides some conditional security in principle, it was proposed by Hoi Kwon, is to filter Alice's signal via teleportation. So the idea is that Bob receives Alice's quantum state, and Bob applies teleportation of that state to another quantum system that Bob has in a more secure sub-laboratory. And in that way, we can deal with side channel attacks. I think this is a promising technique, strategy, but I think it also requires further investigation. In particular, there would be a problem, potential problem, maybe not, that has to be investigated, I think, dealing with the fact that Bob will still generate some pairs of photons. Bob will generate more than one pair of photons, of entangled photons, when trying to apply teleportation, right? When we try to generate a pair of entangled photons, there is a small probability that we generate more than one pair. That's, for example, one of the things to consider, but I think this is some interesting thing to investigate. And I'll just summarize very briefly what we said. So we discussed multiphoton attacks applying to various Mistrustful quantum cryptographic tasks with photonic setups. We show that the commonly used symmetrization of losses is not secure. There are other countermeasures to analyze, which open other problems, as we discussed in our paper. The trivial reporting strategy is the only known perfect protection, but it requires state-of-the-art experimental setups to be useful in practice. And there is no currently any perfect protection against arbitrary side-channel attacks, as far as I understand. Yeah, thank you. Thank you very much for your attention.
Thank you for the talk. Are there any further questions in the audience?
Yes.
Yeah.
Sorry. Sorry.
Yeah.
Yeah, so I was wondering for the symmetrization of losses strategy, you said it's not secure against multi-photon attacks, right? But could you increase the security by just increasing essentially the number of rounds in the protocol so that essentially Bob has a good chance of equalizing detection probabilities within the difference in efficiencies?
You said by increasing the number of rounds?
Yeah,
What do you mean?
The number
Ah,
of detection events and the number of events in the protocol just making arbitrarily large.
okay, okay. So yeah, in that particular task, we consider that there is only one round. So Alice sends only one pulse to Bob. But the attacks, actually, we also discussed in the paper, the attacks could apply to variations of that task where Alice sends various pulses. And yeah, so let me see if I understand your idea. If Alice sends many pulses, let's say tending to infinity, Bob could, the idea of symmetrization of losses, discarding some of the events so that we equalize the detection probabilities. Bob could, and let's assume that Bob achieves perfect probabilities. That still, I mean, yeah, that would help, but still would open still would leave the loophole open because that would only work for, let's say, a particular number of photons that Alice sends. Let's say Alice and Bob agree that Alice, well, usually Alice would send only one photon, and let's say Alice does send that one photon only. If Alice is indeed only sending one photon, Bob could apply symmetrization of losses and guarantee exactly equal detection probabilities. In that case, Alice would not learn Bob's measurement choice. Alice would guess Bob's choice with probability exactly 1/2, so it would be perfectly secure, but only if Alice sends one photon. The problem is that because Alice is dishonest, Alice could change the number of photons. Let's say now she sends 2 photons. For 2 photons, then the probabilities now will be different because the detection probabilities are not linear with the number of photons. So Bob might be able to equalize the probabilities when Alice sends 1 photon, but if Alice changes the statistics and now sends 2 photons, the probabilities will change slightly, and so on for different number of photons. So that technique will not guarantee Bob exactly equal probabilities for an arbitrary number of photons that Alice sends. Yeah, it would work only for a particular.
They're not like Fox states, just that this would be the probability distribution.
Yeah, it could also be that Alice has some, instead of sending, let's say, 1 photon or 2 photons, she has a weak coherence source. So there is some statistics. for a particular quick coherent pulse with a particular average number of photons, Bob could equalize his probabilities, but then Alice might change the average number of photons because she's dishonest, and then that will not work. Yeah. Yeah, thank you that's a very important point to clarify. Thank you for the question. Yeah. Yeah.
Thank you for the talk. I have a few questions. The first one, is it baking for protocol? At the end, Alice and Bob will publicly announce which basis to choose to include measurement for various things. So why are we protecting so what is the point of Bob do not want Alice to know the
Yeah, that's a good point to clarify. Thank you. Yeah, in BB84 protocol, you're talking about the quantum key distribution. So there is Alice and Bob, they trust each other, so they do the protocol as they agreed. They want to protect against Eve, who might learn the key, right? But here we are considering mistrustful quantum cryptography. It's a different, it is about different cryptographic tasks, so it doesn't include quantum key distribution. Here there is only Alice and Bob who do not trust each other. So Bob wants to guarantee the privacy of his measurement. Alice, they will not announce their basis in this particular task because this particular subroutine we discussed is used for other cryptographic tasks in which they don't announce the basis. They want to keep their basis private. Yeah. Yes. Thank you for the question.
Any other questions? Last question.
So in the multi-photon attacks that you mentioned, do you also consider the cases where we have entangled photon states? And for example, Alice keeps some of the state with herself and sends the other part of the ball. Is this also considered?
Yeah. Yes. Thank you for the question. Yes. Yeah, we included those as part of multiphoton attacks. Yeah, Alice could have an ancilla entangled with the pulses that she sends, and the pulses that she sends can also be entangled among themselves. They can be arbitrarily entangled. So in the general results, I mentioned, for example, that if Bob has exactly equal efficiencies, I said Bob has perfect protection against arbitrary multiphoton attacks. That includes those attacks. So all of those attacks are included. And yeah, thanks for the question.
Maybe less than legacy.